Okay, good afternoon. Welcome back. So, going to continue on with some quadratic equation solving by factoring. Let's look at this problem. So we want to solve 3n minus 2 times 4n plus 1 equals 0. We recall this question, this type of question. We don't ever want to balk at the fact that a problem can already be in the form we want it to be in, right? So we want to keep track of what we're being asked to do. We're being asked to find for what values of n is the left-hand side 0. Well, I mean, you can multiply it out. But I think you'll recognize this is not easy to solve, right? Maybe with a graphing calculator, but as it is in that form, 12n squared minus 5n minus 2, no obvious, at least not to me, what numbers to plug in, what n should be to make this 0. You know, it's tough. One thing let me put this in red. There will come a time when you will feel the urge to rewrite this equation like this and then factor and then solve for when, so this means, it's when n equals 2 or when 12n minus 5 equals 2. But that is not the case, right? I'm putting this in red because we very, 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 very importantly need this equal to 0 part to be worrying about factoring. Because the point of factoring, again, is to rewrite an expression in an equivalent way so that you're multiplying two expressions. And since they are equal to 0, or you want to know when they're equal to 0, and anything times 0 is 0, that's why you can look at them separately. The problem here is, in this case, like let n be 2. Oops. Then you get 2 times 24 minus 5, 2 times 19, 38. That's not equal to 2, which is what you're trying to accomplish. It's hard. This type of factoring doesn't actually help you because 2 times anything isn't any particular specific number. Only times 0 equal to 0. Anything times 0 is equal to 0. That's why we're looking to have 0 on one side of the equation. That's why we're able to look at separate factors and assess when they are 0 separately, because it doesn't matter the fact that the other term is non-zero because it's multiplying by 0. So we're going to solve this. N equal 2/3 or n equal negative 1/4. Oh, perfectly fine. This is our first kind of example with two sort of scenarios. One is leading coefficients or coefficients here that are not 1, so 3n and 4n. But it's perfectly fine. It usually leads to a case where you get a fractional answer, but there's no reason why plugging that the zeros have to happen, at whole numbers. Absolutely not necessary. Wherever it happens, that's what we're curious about. And we're going to look at a couple more. So if it's coming pre-factored, great. Great. And we just plug through it. It's already factored. No problem. Now we've looked at some that are not already factored. For example, here's a new one though, little wrinkle. So of course we solve it in the same way, we factor. It happens that this is a square, so x plus 2 times x plus 2, each of the factors is the same. This doesn't impact the strategy, and it doesn't impact the follow-through, though it does look a little bit different, right? So from both of these, we get x equal -2 to be to the time when the left-hand side is equal to 0. Perfectly fine that they're the same number. Sometimes we call this a double root, but ultimately what we want to know right now, though you should think about maybe what this means, and other, especially graphically, has some interesting implications. But basically we're saying that x equals -2 creates a 0, but no other numbers do. So those are some new wrinkles. Let's get into the meat of it though. We want to look at things like this. So what's going on here? We want to know for what values of k is there a balance, an equivalency here, between 3k squared plus 72 and 33 times k. Like for what k's are both of those sides going to be the same number? So we can start to maybe speculate. You can try out some different numbers and get a sense. You might even find the right answer or a right answer in the testing phase. But I think it's important to realize that this is not too far off from just solving something that we're very comfortable solving. Factor, solve, check. The difference here is that, of course, we are always concerned with getting a 0 on one of the sides. What are we saying here? I mean, in essence, we're curious about when, in the first case up here, when this equals this. But if those two things are equal, then they subtract to 0, right? They're the same number, difference is 0. So we can rewrite to say -33k on both sides, subtract it, and it rewrites in this equivalent equation form. Now we're all set. Now we're all set. Small wrinkle, we do want to look for things like this where we can factor out a number, because it makes the polynomial factoring a bit easier. Looking at -8, -3. Now notice something. This 3, while important and a part of the problem, it is not impacted. It is not impacting the final step here of solving. Why is that? Well, for the same reason that we're able to solve them separately in the first place, which is 3 times 0 is 0. So when it comes to this multiplication, if one of these two terms is 0, multiply by 3, multiply by anything, it's still 0. So these are our potential answers, and we can check them. we can check them, and when we check, we should use the original answer, or the original question. We're using k's here, k equal 8. Boy, oh boy, do I know this one. 264, I think. Okay, so I would use a calculator probably to verify that one, but I feel relatively confident. So these are checked. So you can tell maybe as we do this that these questions can get more and more complicated, right? I mean, it's not as though the sort of core of them changes significantly, but like a lot of things, we make a small change here to the setup, a small change here to the setup, and you have to account for those small changes. Maybe this one's not equal to 0, so you have to rearrange it so that it is equal to 0, because we're looking for multiplication problems, and 0 times anything is 0, so we can look at the smaller pieces. Then factoring out the 3 is somewhat interesting. After that, it's solid. Checking, always a good idea to check the original, the thing that you're initially working with, because that accounts for things if you happen to overlook, although we looked at this a bit for rational function simplification, if you overlook a domain issue or if there's squaring involved. So there will be cases where you check an answer that you've gotten by a completely legitimate and correct way, and that answer, in other words, that answer could be wrong. These are potential answers. That the first step here, this first process up to the green, is saying a way of eliminating a huge infinite amount of potential answers down to just a few. Then you want to check to make sure that those few potential candidates are actual answers. They may not be. Solve for k values that make k squared equal to negative 4k minus 4. K equals negative 2. It did in fact check, and that's it. Now let's keep going with our complications here. So 2v squared minus v plus 12. When is that equal to negative 3v squared plus 6v? Well, okay. First, can we restate what we're being asked? for what values of v, if any, does negative 2 times v squared minus v plus 12 equal negative 3v squared plus 6v? Well, v can be any real number, and as v changes, both left and right side are fluctuating. They're both in change. So, plug in v equals 0, for example. You get 12 on the left-hand side, 0 on the right-hand side. They're not equal at 0. Okay. What about 1? Well, on the left-hand side, I'm looking at 9. On the right-hand side, I'm looking at 3. Not equal. Okay. So this is the idea. What we're really trying to wonder about is, are there any values of v where they are equal? And the strategy is generally going to be one of two things, either looking at the graphs for where they cross each other or solving algebraically when possible. So what I'm going to do is I would like to make the right-hand side be 0. And in order to do that, I need to keep that balance. So this is kind of what we're doing with these algebraic rewrites. What we're trying to establish is that negative 2 times v squared minus v plus 12 is negative 3 times that same v squared plus 6v, precisely when v squared minus 7v plus 12 is 0. And we've done this by maintaining the balance here. We're getting this equivalent alterations to both sides of the equal sign. I've always been partial to the idea of a balance here. You have, say, a bunch of different blocks on the left and right side of a balance, and they're perfectly equal. If you take off blocks or add on blocks that are also equal, then it will stay balanced. And that's what we're doing in this process. We are taking off and putting on blocks, different sizes, but equal on both sides. So we're going to add a 3v squared block on the right and on the left. We're going to take away a 6v on the right and on the left. And therefore we maintain the equivalency. Oops. This factors. So for now, I'll just show you that one check. You should also check 3. But for time's sake, I'll leave that to you. Okay. This one, absolutely a calculator for me. Now, I think it's important again to say that that there are small differences, but can we appreciate the spirit of what we're doing with this and why we factor, right? And why we have it equal to 0. It all harkens back to the idea of we are able to rewrite the expressions, maintaining the balance of the equation to set it equal to 0. And if that factors, then we can do this by hand and say, oh, okay, well, then if either factor is 0, the overall multiplication is also 0. So that is the heart of what we're doing here. This is 100% something that you should practice, solving quadratic equations. There's more to it. There are more layers. There are other strategies, things that don't factor well. For example, quadratic equation you may have dealt with, lots of different options, and we'll look at some of those as we move forward.